from their CAIAS, and he will talk to us about 5D superconformal index with enhanced E-type global symmetries. Thank you very much.
All right, thank you very much for giving me a chance to present our recent work. We hope to finish the paper in a few days. This work has been done with Dr. Hichul Kim and Sung-Soo Kim of CAIAS, and I guess we spent about 4 months to come to this point. Right, so today's topic is 5D superconformal index, and the people have been doing a lot of calculation in 3D, 4D, and we decided to go other direction, 5D and hopefully 6D. So some time ago, Cyborg proposed 5D superconformal field theory. And let me briefly review his conjecture on this 5D superconformal field theory, which arises from, say, you can produce that from any perspective. One is a brane picture, and one can start with SO32 type 1 open string theory and compactifying on a circle, and then TDL it. Then one ends up with this O9 brane becomes a 2O8 branes, and because your gauge group is SO32, you have 16 D8 branes between these intervals. So you end up with type 1 prime theory on 9-dimensional width interval, and there will be a 16 D8 branes between them. And there will be a 16 Wilson lines giving us the location of these D8 branes. Now we can choose coupling such that this interval is very large, and then put NF D8 branes at one of the oriented field, and then we introduce one single D4 brane as a probe, exploring the physics around the one end. Now, physics on D4 brane, because of oriented fold, is 5D n equal 1 super Yang-Mills theory with SP1, which is SU2 gauge group. And also because you have NF D8 branes, there is NF fundamental hypermultiplet connecting D8 and D4. And this 5-dimensional Yang-Mills theory in Coulomb branch has the expectation value which is diagonal. That's a 2x2 matrix. And this one is a single scalar field. This use Weil vector and make a diagonal value to be positive, and then this value indicates the position of a D4 brane along this interval. Now, one can do the one-loop correction to the kinetic energy, and turns out there is parity the contribution to the kinetic energy given in terms of this Chern-Simons terms in U1 gauge theories, because you break SU2 to U1 by going to the Coulomb phase. And the effective coupling, because this Chern-Simons term-like term is basically a Yang-Mills term with coupling constant depending on position of scalar field, one gets effective coupling constant given in terms of classical value, and 8A comes from vector multiple contributions, and then minus contribution coming from the these hypermultiple contributions. And the MI, even though we at the end put all the D8 brane at the end of the this interval, if we separate D8 brane from the this end, then this MI is the mass of the hypermultiplet, and their contribution come in this way. Right, so this MI, which is mass of the hypermultiplet, is the position of D8 branes from this orange point. So one can choose MI to be all 0 by putting D8 brane at the end. The effective coupling will be given in terms of classical contribution plus one contribution. So we are looking at the limit where this classical contribution is equal to 0. It means we are choosing coupling constant to be infinite, so that there is no bare coupling constant. In some sense, infinite coupling kills off the kinetic energy. So we choose bare coupling constant to be infinite coupling. And then we go to the symmetric phase. So we make D4 brane position to be approaching the end of this interval. So the A becomes 0. Then effective coupling constant goes to infinite, and 1 over coupling constant becomes 0. That's the conformal point Cyborg has explored about 1997, so about 15 years ago. And he produced the string theory argument, which I'll briefly review later, that D4 brane physics makes sense even with infinite coupling constant, and the global symmetry of the theory, which you have SO2 and F flavor symmetry, because SU2 is pseudo real, so one can enhance the SU and F flavor symmetry to SO2 and F flavor symmetry, and then you have U1 symmetry coming from instanton numbers, and these two numbers are combined into exceptional groups. So that's what he has proposed. So, for example, this NF plus 1 number of flavor can go from 0 to 7, and there are E8, E7, E6, and this series of exceptional groups, which can be obtained by starting from E8 branes, then cutting off the roots, and then we can reduce to these lower exceptional groups. Now, there's a duality between type 1 prime and heterodyc E8 cross E8 on S1, because heterodyc string theory E8 cross E8 comes from M theory with end of M theory on an interval. And the type 1 prime is basically, again, the type 2 A theory on an interval. So there's obvious duality between them. And one way of getting this duality is that split from type 1 prime point of view, 16 D8 brane into the 7 plus 9 or 7 plus 7 plus 2, and then put the 2 of the 7 D8 branes at the end, and then put the rest in the middle and go to infinite coupling constant. Then there's additional matrices degrees of freedom, which enhances symmetry at the end to E8 gauge group. So this additional enhancement comes from having a new matrix degrees of freedom, which is the D0 brane in type 1 prime, which is a D1 string in type 1 theories. So, but we are not going to the E8 cross E8, we are just going to the E8 symmetry only in one end. So we just care about one side, and then again we put 7 D8 branes at the end, and then we choose type 1 prime coupling constant such that end of the world effective coupling goes to infinite, and then we end up with E8 symmetries. And the one reason the enhancement comes is because of this SO14 symmetry on the 78 brane with O8 brane plus instantons. And the instantons contributed to this E8 representation, with single instanton as a spinel representation of E8, and also two instanton as a 14-dimensional fundamental representation. So then one can use Wilson line to break E8 to lesser smaller exceptional groups. So that's how one get this enhancement of supersymmetry and global symmetry using this type 1 prime and heterotic dualities. So once you have that enhancement, then introducing D4 brane to that one hand should see that enhancement of global symmetries. Right, so the goal today is to see this enhancement of global symmetry on 5-dimensional Yang-Mills theory with SU2 gauge group with NF flavors. And for example, in this Yang-Mills theory, before you go to conformal limit, besides ordinary matrix particles, one has instantons as solitons, and instantons has fermionic zero modes. One of K-genome zero modes produce this charged massive tensor multiplet, and also fundamental flavors has zero mode, which doesn't produce spins but just introduce a flavor spinor representation to the instantons. And the instanton current is the addition of this U1 conserved current is given simply as a dual of the this topological current, topological charge. So we have this 5D Yang-Mills theory with vector multiplet and hypermultiplet, which has SO2 and vector representation. And then we have instantons. So global symmetry is SO2MF cross U1, and our KG group is SU2 or SP1. So this theory as a Yang-Mills theory is not conformal, but we want to go to conformal limit, which means coupling constant goes to infinite, so that Yang-Mills coupling, Yang-Mills kinetic term is disappearing from the Lagrangian. And in that theory, we want to calculate the index. Right, so 5D n equal 1 superconformal symmetry has been studied many times, and superconformal symmetry is called F4, whose bosonic subgroup is made of the bosonic conformal symmetry SO2 and then SU2 R symmetries. So it is made of 8 Poincare supercharges and 8 superconformal supercharges, and superalgebra is satisfying these computation relations. And especially we are sort of out of this spatial Lorentz transformation, we can see the spatial rotation is SO4, which is made of SU2 cross SU2, and in some sense we are lacking one of SU2 with SU2R symmetry. So we are choosing supercharge which carries both one of SU2 or spatial index with this R charge index. And once we choose these supercharges, then their commutation relation is conformal dimension minus this spatial angular momentum and the R charges. And one can see that Q and S from this table is commuting with these commutation relations. So we are looking at the state where this commutation relation is equal to 0. So we are looking at basically PPS state. And so we are looking at this superconformal index, which is basically Witten index, but we are looking at a sector where this term is equal to 0. And then we are introducing various chemical potentials, which commutes with our choice of supercharges. So we have T plus JR, and then there's angular momentum related to SU21, which we haven't used for this choice of supercharges, and then various mass term for the hypermultiplets or flavor symmetries. So that's the quantity we want to calculate for this 5D superconformal series with infinite Yang-Mills coupling constant. Right, so natural way to calculate this index is using the radial quantization and define the theory on S1 cross S4. And well, let me show briefly that when you take an infinite coupling constant limit, Yang-Mills term is not obviously disappears from the theory, but one could have a supersymmetric Chern-Simons term which is conformal. Unfortunately, or fortunately for SP1, this non-abelian Chern-Simons term vanished because it 3-index symmetric structure constant is equal to 0 for SP1. And the hypermultiple kinetic Lagrangian is obviously conformal because it's quadratic in quadratic in hypermultiplet, and one can give a dimension of the fields, and then one can make it to be naturally conformal. Even though tensor term vanishes, one can give a dimension to this vector multiplet field, and then obviously in standard way, then this has conformal in terms of dimensions. So one can have a well-defined conformal field theory. So basically, our theory will be there's no Chern-Simons term, no Yang-Mills term, and we have this hypermultiplet, and that's the theory we have. But we have to integrate over all the gauge field multiplet and also all the hypermultiplets. And this is somewhat similar to, say, CPM model in terms of gauge theories, where there's no kinetic term for gauge field, but we are integrating over gauge field to give a constraint or to remove the phase of matter field. But here now, this conformal Lagrangian, there's no broken phase, so it is at the symmetric phase. So integrating over the gauge field degrees of freedom is really very strongly interacting, very strong constraint to the system. And there's a natural way of generalizing this standard way of generalizing supersymmetric transformation on R5 to R cross S4, which I just wrote down here. Now, to calculate this index, there are many ways of doing it, but natural way is deform the Lagrangian. And first step is shift the time derivative using observing the chemical potentials, and then using this time derivative, one can write down the again original Lagrangian, and then all the chemical potential is absorbed into naturally to the path integrals, and then one introduces killing back spinors corresponding to the supercharge we thought about, and this supercharge is this killing spinor is made of obviously Q and these conformal transformation factors, and the scale of the supersymmetric transformation is exactly what we hoped for. By shifting these time derivatives, we get all the chemical potential we want. And then Q-exact deformation can be written, again, this is very well studied by Pastun and Okuda et al. And one can find the saddle point of this Q-exact deformed Lagrangian, or from the formulaic supersymmetric transformation, and this saddle point integration is localized at the north and south pole contributions. So even though we set up the elaborate procedure, at the end the calculation is localized at north pole and south pole contributions. And this is exactly what Pastun did for S4 partition functions, and we are generalizing that to just S1 cross S4. Now, there are two kinds of contributions to these localized calculations. One comes from perturbative calculation, and this one loop of deformed actions, and further detailed exploration of this perturbative calculation is done by Gomez, Okuda, and Pastun. And again, this perturbative correction also is localized at north and south pole, and there are two contributions, vector multiplet contributions, and hypermultiplet contributions, and at each north pole and on south pole. And it's interesting thing is this vector multiplet contribution has also a term related to Harmed or Van der Waals determinant. So,
it means to do a one-loop calculation when the coupling is infinite?
right, because you are coupling is infinite, but you are doing quadratic integration, then this parameter is overall scale.
So
You
you
can-
said so.
Right, so suppose we have a coupling. So there are two things. Of course, we made a coupling to be going to infinite.
Yeah.
Then we did a Q deformation. Then Q deformed the Lagrangian I didn't bother to write down, which is rather complicated. And this one has a parameter T. And that Q deformed Lagrangian is somewhat similar to Yang-Mills Lagrangian, but which is really different because some of the components is depending on coordinate. Now, in large T limit, the main contribution comes from the kinetic energy because quadratic part, you can observe the T. That's why you have one contribution coming from the kinetic energy. So, right, so you have this perturbative contribution from that quadratic part of the deformed, Q deformed Lagrangian. So south pole just flip the chemical potentials and they give you the same thing, so we get a factor 2. So we have to sum of the all possible saddle points of this deformed Lagrangian, and it will be made of just one contributions, perturbative contribution plus square of the instanton contributions. And instanton contribution from north and south pole are like north pole has instanton contribution and south pole has anti-instanton contributions. So they come with a square. So end result is we have to, this index we are calculating has to be integrated over Wilson line over SP1 along the circle. So we have integration. And then all this perturbative index and instanton index is, some of them are carrying SP1 charges, so they are depending on SP1 holonomies. Okay, so instanton contribution now is made of no instanton contribution, which will be 1, and a single instanton contribution, 2 instanton contribution, and so on. So Q is chemical potential for counting instanton numbers. So as I said, instanton contribution has been extensively studied by Nekrasov and Okounkov, Shadkin, Okuda, Pestun, and ourselves with Sungjae and so recently. And we use all this technology, and we haven't completely mastered, but we can see, we understand enough of it to figure out what's the answer. And so,
the future paper.
Yeah.
You cited the future paper by Nekrasov and
did I give you wrong date?
2014.
Where?
Nekrasov and Shevchin, 2014.
Oh, sorry, right. Right, obviously it was error there. Right, so let me just go over the SP1, ADHM technology for SP1, which is SE2. And turns out this was developed by Columbia group about 30 years ago. And it's much simpler than SE2 case. And basically ADHM data, probably you heard of WAL, is made for SPN is because this simplex group, one can make it to be a little simpler. So instead of, say, for example, this B mu for SUN case, n instant, B mu will be K by K Hermitian matrix, but because K group is SPN, this K by K symmetric real matrix. So it's much less information, which means data is simpler. And also this term SPN is part of SU2N. So it's a 2n by k, 2k matrix, and again one can in terms of quaternionic, and this real matrix instead of complex matrix. So data is smaller. So it turns out that Columbia group has found the exact solution for the 3 instanton case using this one. Usually that's the end of that 3 instanton express ADHM solutions, but they found it in the original paper. So this once you have this data, this should be del dega del should be invertible k by k matrix, and this gives a okay d-term constraint on these data. And then once we have this delta, then one can find the v, which is again m plus k times n real vectors, so that from which satisfying this property, then we can construct a gauge field. And because this real vectors again, one can show A is traceless and also belongs to SPN. Usually in SUN case, this is not traceless and it's UN field, and so it's SPN ADHM data is simpler. And one can do the parameter counting, it works. And the interesting thing is the gauge group on ADHM data is not SOK, but it's OK. So it will be very, very important. So OK is the SOK element plus K by K matrix whose determinant is equal to -1. And this will be crucial in our further discussions. One of the reasons is that there are more symmetries on this data than SOK. OK modding out of this data leaves the gauge field invariant. So this is not good enough. To get an instanton partition index, we have to go to digital dynamics. And this long stories, and we turn on the chemical potential, and we use our work and Leclerc-Superconformal Shadchin's work. And we do localization. And then at the end, because our dynamics on instanton dynamics on K instantons is OK variables, at the end one has to integrate over OK Cartan variables, which is depending on K is even or odd. One can write down K equals 2n plus chi, and chi could be 0 and 1, and this diagonal element of the Cartan element of OK. And then one has to integrate over this Wilson line of the OK, SOK Cartan element. So, and this is made of several pieces, and that this work was done by Leclerc-Superconformal Shadchin, and then we modified that to OKKs. So here's the various terms. There's measure terms, and there are various contributions coming from ADHM constraint, and the terms coming from fluctuations. It's made of whole machine is producing these terms, and then K index for K instanton is given as integration over this Wilson line of OK groups. And especially interesting is K equal to 1, there's no integrals. K equal to 2 and 3, there's single integrals, so it's more manageable. Now let's look at single instanton contributions. And the SO1 index is given in this form. And then you go through each contributions and then see what happened to the because SO1 is just the identity transformation, but O1 is the transformation which changes any fundamental representation to -1 of that fundamental representation. And then by looking at that, and one can see some of them, it has to be averaged for 1 and -1, and then some of contribution has to change from sine to cosine. So this is the contribution for O1 case for single instantons. And then we can look at there are various chemical potentials. So we can turn off chemical potential, and looking at the leading term in expansion in these x variables, and one can see this single instant correction just give you 1 plus 2 nf minus 1 q plus q inverse x cube, and q is for instanton, q inverse for anti-instantons. 2 to nf minus 1 is exactly the spinel representation of the SO2nf, and so that's the single instant contribution. It has a lot more terms, so it will produce a lot more terms. For two instantons, it's more complicated. So it's given in terms of single integral, and then there is a whole contribution coming from the vector multiplet plus spread multiplet. So this meta hypermultiplet gives a very simple expression at the numerator. Now, generalizing this to O2 index is again complicated. We have to look over every term and then see which one changes the sign. So that's the contribution we have. And then this integration, and there are many folds along the line. We deform the gamma 1 chemical potential by putting infinitesimal imaginary terms, and then we are doing what's called control integration in terms of zeta, and there are poles for this control, and this additional part for O2 is independent of this control integration, so it doesn't contribute. And interesting thing is that if you look at these meta contributions, then in terms of depth variables, the pole structure is that when flavor is near the zero, is given in this form. So dz over z times 6 minus nf. So because of there are 2s and 1s, in terms of phi coordinate, one can collect, and it's z to 6 minus nf. So you can see that if flavor is 5 or less, then there's no pole at z equal to 0. So there's no issue. However, if flavor is 6 or 7, then there's pole. And once you have pole, then you have to take away, then that process is not consistent with O2, so we don't know which one we have to add when flavor is 6 or 7. And it will be cause of the trouble for us. And so leading term index, there's perturbative part and the instanton part. So if you look at just the x cubed term, there is 1 plus ordinary representation of SO2NF times x cubed. And the instanton part, I said that this coming from spring representations with instanton and anti-instantons. And interestingly, if you look at just leading terms, then there's 1 plus this term, and they are combined into 1 plus, combined into ordinary representation of this exceptional group. It's E NF plus 1 for NF less than 5. But this standard decomposition of the exceptional group into the 1 less, small less, or 2NF plus U1, we went through the Slensky's physics report. I don't know you know about it. And there are all kinds of data, and we mined quite a bit of that. So NF less than 5, it works for x cubed. And high order we'll see. And then there are high order in x with full chemical potentials. There are multiple instantons, and then NF equals 7 and 8. Those are certain cases. So full index calculation, we have to expand in power of x and collect all the chemical potential and express them as a character for the enhanced global symmetries. So for example, of course, mathematical does work for you once you use it. This is a small part of our mathematical program to produce characters, and we've been able to produce quite a number of characters. So let's go over to the simple case, NF equal to 3, then because less than NF equal to 2 and 1 is rather trivial, perturbed part is given by that, instanton part is given, and then this, as I said, the x cubic term is related to E4, which is SU5 ordinary representation, so they have a nice decomposition and number comes out right. And one can turn on the chemical potential, then Y chemical potential, there is x9 over 2, x6, and there are all kinds of terms arising. We checked the x9, and all of them can be expressed in terms of characters of E4. And interestingly, in this case, there are, for example, two instanton corrections, single instanton corrections, and so on. So this is a rather non-trivial calculation, and we got the character for E4. So NF equal to 4. Again, we got the index in terms of characters of E5. And again, in this composition, there are 2 instanton contributions and single instanton contributions. And we are still working on 3 instanton contributions and making some progress. Now, NF equal to 5 is the place still we are safe. And again, we produced all the index of E6. And this is, for example, the composition table of the various representations. So one of these 43, 75, 8 dimensional representation. Of course, we didn't know about this until we are working on it, and then decomposing this in terms of SO10 cross U1, and that's the decomposition. Characters from each contribution combine into characters for E6.
So is there an interpretation for index? So is it?
Oh, of course, that's interesting. I mean, we have a calculation. So question is what these things mean. Of course, we have no idea. Obviously, you do have some serious interpretation or implication in some more extended context.
Because it might be, you could probably connect it to, say, the heterotic string, where
And also,
there is a sort of a notion of what instantons mean in that context.
Right. Also, this is related to the compactification of theory on Telpetros, Calabi-Yau with Telpetros singularity. So it tells something about Telpetros space also. So it's probably counting some curves on Telpetros space or something, which I have no idea. Right. So this using our index calculation, this is the thing we can do. But we can do a little more for E7 and E8, even though our integration got stuck. For example, alternative representation for E7, not like until E6, everything is done in some single instantons and the alternative representation coming from the hypermultiplet and the anti-hypermultiplet. But E7, we have two instanton contributions. E8, also we have two instanton contributions. Those are the cost of the travel. However, we can study the index structure, and then we can make a conjecture about E7 and E8 index, even though we don't have the derivation. For flavor less than equal to 5, we can represent in terms of some alternative representation. Interestingly, even though what should I say? The hypermultiplet comes with fundamental representation. We are looking at KD invariant quantities, so it is always combined with anti-hypermultiplet such that it's sort of singlet or alternative representation. And turns out that when NF is less than 5, this index is given in terms of everything made of the alternative representation, and there's symmetrization, anti-symmetrization, and so on. So one can express of this extended exceptional groups. So this is the expression we wrote down, we found for index in terms of this alternative representation. So once we have this formula, then we can just pretend this group is E7 or E8. And then one can write down the index. And of course, this is conjecture, and we don't know whether, we have to confirm that. And we don't have the technology to confirm our conjecture yet. All right, so let me conclude. So Seiberg's conjecture for the enhancement of the global symmetry is confirmed by index calculation for flavor less than or equal to 5. And for NF equal to 6 and 7, we need a further understanding of multi-instanton corrections, even though we have provided a conjecture for the index. Now, one can think about, instead of SP1, one can introduce multiplicity for branes, so 5-dimensional KG group can be increased, and one can do the similar calculation. And sometimes this index, these theories have a Higgs branch, and the Higgs branch is basically instanton moduli space for E-type of E-type. So recently there have been some work on the calculation which one relates to instanton moduli of exceptional groups, and our work is also further exploration of that aspect. So there is obviously, our work is saying something about this. And also, one can relate by going back to the lower dimensions, or one can go to higher dimensions. Especially one can, because now we have certain technology, one can expand that technology to index calculation in 6 dimensions with 1,0 superconformal field series. And of course, the ultimate holy grail is at this game, maybe, is index of the 2,0 theory in 6 dimensions. And we hope to challenge this aspect in the near future. Thank you.
Questions?
So the problem is the integrals.
Right.
Like, can you at least have some numerical test of whether
Integrals.
whether, because you have a conjecture of whether
Right.
this result should be. Can you let's check whether this.
Integration you can do, but power singularity comes with is the problem. So we have been trying to improvise this integral from z equal to 0 and trying to conjecture it, correct it, but we haven't been successful.
I'm interested in the last thing.
Of course.
So, can you really, well, I mean, there's the paper you wrote with Sanjay where you had the 5D
Right.
Mills index that you then lift in some sense.
Right.
Can you calculate directly in the 6D theory something?
Well, we don't have a theory, so, but
Yeah, I said something.
right, something. So it turns out there may be a way to do it. Not the partition function, but index maybe,
Yeah, that's what, because
Right.
you're doing an index. You
Right.
don't need as much.
because you have S1 consists 5. And so it just, this one, I can see how can it be done. And then it's telling us something that maybe you can do this too without much difficulty. So there is something I can see maybe one can proceed from. So once we have enough Greek, then why bother with this? We can go there directly, right? So we'll see.
Anyone else? Okay, well, thanks, speaker again.
Right, thank you.